Hello, my name is Ben Campbell, and today I'm going to be talking about on-orbit polymer degradation results from MakerSat-1, the first spacecraft designed to be additively manufactured in space. Now, this is a CubeSat project professors and students at Northwest Nazarene University have been working on now for approximately 6 years. Currently, orbital manufacturing has only been a dream for the future and doesn't quite yet exist today. At the moment, production is limited to ground-constructed components being fully assembled on Earth and then launched into orbit. However, now some new equipment is available to begin experimenting with orbital spacecraft construction, utilizing 3D printing technology available aboard the ISS as a means of enabling this concept. Made in Space's additive manufacturing facility is a 3D printer which is able to print custom, on-demand plastic components aboard the ISS in microgravity, which can be used to make things such as tools or other hardware for different experiments and tasks done around the station. So now, what if rather than printing just custom on-demand tools and hardware on the International Space Station, what if we were also to 3D print ISS deployable spacecraft structures as well? This new capability of producing custom components off the ground can allow for optimized spacecraft design compared to today's ground-based manufacturing techniques. With ground-built satellites, they need to be designed to withstand the intense ride to space, and they are subjected to high forces and vibrations. After this relatively short-lived launch process, however, these satellites only require minimal structural integrity to hold themselves together for the majority of their operational lives in orbit. So, what if we were able to eliminate this need for extreme durability and structural complexity and instead reap the benefits of optimized, simpler to produce structures for spacecraft? Well, a team at Northwest Nazarene University decided to make a plan to make that happen. So here is our big concept on how spacecraft could be manufactured in space. In the ideal process for construction of an orbitally manufactured spacecraft, such as our satellite MakerSat-1, it would have its simplified structural frame components 3D printed aboard the ISS. Then, electrical boards would be assembled on the ground and launched in a smaller package by both weight and size to the station to be unloaded. Upon the arrival of these electrical components, they would be mated with the 3D printed plastic components aboard the station and then deployed into orbit as a functional CubeSat ready for operation. Now, currently, 3D printing metal structures in space isn't exactly possible yet, but it is possible to print with polymer plastics. However, one disadvantage of using polymer plastics in space is that they degrade over time in space. These weaker materials are ravaged by the environmental factors present in space, and they need to be studied prior to deploying 3D printed satellites into use. Some of the different factors that can affect polymer plastics in space include extreme temperatures, radiation, outgassing, and oxygen plasma erosion. Now, some research has been done on polymer durability in space, such as a project known as the MISSI-2 Peace Polymers experiment in the early 2000s. In this project, a variety of different polymer samples were positioned on a rack just outside the ISS and then left exposed to space over several years. The picture in the upper right is of these samples prior to deployment, and then the picture below is how these polymers looked after a few years of exposure in space, highlighting the extremity of polymer degradation. And while this experiment was a great source of new knowledge, no research such as this had yet been done on 3D printed polymers prior to the start of the MakerSat missions back in 2014. So, before applying this concept of orbital manufacturing with polymer plastics, some questions have to be answered first. First is the question of how fast these plastics degrade in space and whether they would be suitable for use in long-duration spaceflight. One factor that can be measured to determine the level of degradation is mass loss, where which mass decreases along with the structural integrity in a structure. Knowing how much degradation different polymers experience is another key problem to be tackled. Also, among the wide variety of different printable materials, what kinds would best be utilized for spacecraft construction? NNU students then set out to investigate some solutions to these problems with the MakerSat project. Over the past 6 years, NNU students and professors have developed two 1U CubeSats to test the durability of 3D printed polymers after long-term exposure in space, called MakerSat-0 and MakerSat-1. So first, I'll explain a little bit of the theory about how these spacecraft were designed to evaluate polymer degradation in space, which was done by a process of recording polymer mass loss over long-duration spaceflight. To measure the mass of a polymer sample in a microgravity environment, the MakerSat team utilized a system involving piezoelectric cantilevers, which would be mounted to a vibrationally excited base on one end and then suspend a polymer sample on the other end. By recording the resonant frequency of the cantilever and incorporating the physical constants associated with the cantilever itself, the effective mass suspended at the end can be calculated. This concept of mass measurement in space was replicated on both MakerSat-0 and MakerSat-1. By having a vibration motor connected to the same baseboard as a set of cantilevers, measurements would be made as the motor would sweep through a spectrum of frequencies far above and far below each cantilever's natural resonant frequency, and then determine the resonant frequency within that range to be communicated to the ground. Polymer cantilever frequencies are also compared to those recorded by a bare cantilever equipped with a brass mass sample, a theoretical control mass which would not change over time. Using a control cantilever helps to filter out some of the physical effects on the cantilevers, such as vacuum and temperature variations. The cantilever measurements on the MakerSat-1 system have a frequency resolution of around plus or minus 0.2 Hz, and thus a calculated mass resolution close to plus or minus 1 milligram with our specific cantilevers. So, the MakerSat project began with the development of MakerSat-0, a spacecraft built as a typical 1U CubeSat with an aluminum frame and fasteners, and set out to study 3D printed ABS, PLA, nylon, and PEI samples in space. It was launched back in 2017, and the spacecraft was operational for a few weeks prior to an electrical complication with a damaged solar panel. Now, this was our very first CubeSat mission, and the experience taught our team a lot prior to the flight of MakerSat-1. The results from this mission are discussed in NNU's 2018 SmallSat presentation and paper on MakerSat-0. Now, MakerSat-1 was developed to mimic the same functions and electronic architecture as MakerSat-0, but instead with a 3D printed frame. Some other improvements were also made to the MakerSat-1 hardware based on the team's experience with MakerSat-0, which led to new features such as better solar panels, electrical batteries, and communication systems. Now, the MakerSat-1 system was designed to be easily assembled by hand without the need for any tools or fasteners. Its simple design can be easily assembled within 10 minutes, saving valuable ISS crew time. Now, here on the left, we have our flat-sat origami-like configuration where the electrical hardware is all wired together, yet not in its final physical form. Then on the right, we have a conceptual CAD model of how these electrical boards would be folded and snapped together. So now MakerSat-1 uses a system of 4 3D printed rails as the main structure to hold the spacecraft together and can be easily snap assembled. Now here on the left, we have a partial assembly utilizing our rail design, and then on the right, we have a more detailed view of these self-locking rails which hold the CubeSat together. With this design, in 2017, a big day was able to occur for the team where, after years of work, the structure of MakerSat-1 was able to be printed aboard the ISS using 3D CAD models developed and uploaded to the station by NNU students. After they were finished printing, the crew was kind enough to be able to display the parts by the cupola module window. Here on the left, we have the rail components, and then on the right, we have a little NNU-themed rail holder. In all honesty, it was pretty cool being able to be a part of an undergraduate team and being able to have our own custom spacecraft hardware manufactured aboard the International Space Station. Now, unfortunately in our case, we were not permitted to proceed with our original mission plan for MakerSat-1 due to the process of manual CubeSat deployer loading on the station being disallowed by NASA's safety panel. Our original plan, including the process of crew assembly, was permitted by the panel, but it was not able to be practiced after years of waiting for loader permission changes. The team then had to work with a ground-assembled MakerSat-1, not assembled by the ISS crew for deployment. And yes, this was a bit of an unhappy deviation from our original plan, but we learned to work with it and move on. This caused for a slight mechanical redesign of MakerSat-1, and despite this situation, MakerSat-1 was able to pass pre-flight vibe tests and was able to be launched to the ISS with a 3D printed frame. Here on the right, we have the last photo of MakerSat-1 as it was loaded into the SEOPS slingshot deployer after hardware handoff. In the future, however, if NASA's safety panel were to ease some restrictions for manual deployer loading, this CubeSat could have been manually assembled, loaded, and deployed in orbit. Then, MakerSat-1 was launched to the ISS on a resupply mission, the SpaceX CRS-19 flight in December of 2019. Our team was also able to enjoy being able to watch this final launch together at Cape Canaveral, Florida. Following the arrival to the ISS and a 2-month stowage period, MakerSat-1 and its deployer was mounted to the Cygnus spacecraft hatch door by the ISS crew shown here on the left. Cygnus was then unberthed from the station on January 31st, and then MakerSat-1 was deployed from Cygnus on February 1st, 2020, and has been in operational orbit since that time. Now we can get to some of the critical science data that has been able to be retrieved from the MakerSat-1 flight so far. It has continued to remain operational since deployment, and to the date of this presentation being recorded, has communicated 4 months of processed data from low Earth orbit on the effects of space on its 3D printed polymer samples of ABS, PLA, and PEI plastics. Now, as previously mentioned, the polymer mass degradation experiment uses a cantilever motor setup in which a sweep of frequencies is applied to cantilevers, and the resonant frequencies of each cantilever are recorded in the process and used for mass calculation. The raw data retrieved from the CubeSat include time domain and frequency domain amplitude data, producing figures such as the sine wave on the left and the resonance plot on the right. Plots relating frequencies and measured maximum amplitudes result in peaks where the system reaches resonance, and the frequencies where these amplitude peaks occur are recorded onboard MakerSat-1 and communicated to the ground for later processing. The results from this process are on the next few slides. For these plots, the data was taken from a cantilever loaded with an ABS sample. Here on the left is the recorded normalized resonant frequency for that cantilever versus time in orbit, and then on the right we have the corresponding normalized polymer mass versus time in orbit. This type of data was also taken for the other two samples, PEI and PLA. When comparing all three of these plots for polymer mass loss, it can be visibly seen that ABS and PEI experienced rapid mass loss during the initial couple weeks into flight, which our team suggests is likely due to UV-assisted outgassing. PLA, however, while still losing mass, did not experience as great of an initial mass loss rate as the other two samples did. After a few weeks, all the samples showed slower and near-linear mass loss rates, which are suspected to be caused primarily by oxygen plasma erosion. Then here is a summary table on each polymer sample listed on the left-hand side at different instances in MakerSat-1's flight lifetime so far. There is information on normalized frequency, total suspended mass, polymer mass, and percent mass loss for instances prior to flight, just a few days after deployment, 2 weeks after deployment, and then the most recently processed data. The cells highlighted in red indicate the percent mass loss for each sample at each listed instance in time. Overall, in the course of MakerSat-1's current 4-month lifetime, the most resilient material so far has been PLA, experiencing only around 9.9% mass loss, while the other two materials have degraded even further, with PEI having around 20.9% loss and ABS having around 26.5% loss. It is suspected that the durability of these materials is loosely related to each material's density, where higher density materials such as PLA are more durable than those of lower densities like ABS. From the data recorded from flight, it appears that PLA plastic has the lowest amount of initial mass loss. These results match the data retrieved from MakerSat-0, reinforcing our initial conclusions. But given the longer session of data from MakerSat-1, however, we've been able to study degradation rates on a longer timescale, revealing that after initial outgassing behavior, PEI has a slower long-term erosion rate. Using extrapolated figures, this shows a possibility that PLA may be better suited for short-term missions, and then PEI may be better for longer duration missions. With the MakerSat mission, we've been able to pave one step in the path towards the field of orbital manufacturing. If humanity continues to extend its reach out into space, soon manufacturing everything on the ground may become impractical for some applications. By taking steps towards off-world manufacturing techniques, soon the space industry may become independent of ground-based manufacturing and reap the benefits of creating optimized, on-demand hardware while in space. We'd like to give a very warm thank you to all the people who have been a part of this project who, with their generous guidance, assistance, and support, all helped get the MakerSat project off the ground over these last 6 years of work. We'd like to thank the Idaho Space Grant Consortium, Jeff Fitch and Michael Johnson from CEOPS, Jeff Daly from Near Space Launch, Dave Paulus from Plexus, Matt Napoli from Made in Space, Scott Higginbotham from NASA, Dennis Satiro and his students from Caldwell High School and Northwest Nazarene University. And with that, we'd also like to say thank you to you for listening to this presentation. Now, given the nature of our presentation being pre-recorded, we aren't exactly able to answer live questions. But that doesn't mean we aren't enthusiastic to answer your questions at any of these points of contact, such as my email listed here at the top. Thank you, God bless you all, and we hope you all have a great rest of your day.